Welcome, aspirants, to another explainer from Rungta IAS Academy. Today, we're unpacking a highly critical topic for your General Studies Paper 3 syllabus, right where science and technology meets disaster management. We're talking about induced seismicity. Exactly right. Now, usually, seismology is all about predicting or surviving natural earthquakes, isn't it? But today, we're examining a truly fascinating, deeply counterintuitive scenario where scientists are actually trying to trigger them.
Okay, let's dive into this. Imagine a UPSC interview panel throws this at you. Why on earth would scientists deliberately initiate a natural disaster? It's a real paradox. Typically, researchers just place sensors near fault lines and passively wait for the Earth to move. But the research we're analyzing today, it completely flips that approach. They are going deep underground to actively provoke the Earth.
Right, and to really contextualize this geographically, let's look at the location. This experiment happens at the very end of a 5.2-kilometer ventilation tunnel leading to the Furka railway tunnel over in Switzerland. We're talking about an environment situated incredibly deep within the Earth's crust, far removed from the surface, where geological forces are just massive and untamed.
And that brings us down into the BedrettoLab. The isolation here is absolutely profound, students. Imagine 1.5 kilometers of solid mountain rock pressing directly overhead. You can only reach it using these specially adapted electric vehicles driving over a muddy dirt floor.
Exactly. And Dr. Giardini, the lead researcher here, considers this extreme, hyper-controlled environment the absolute perfect methodology for in-situ geological testing. It's what allows these scientists to closely monitor fault dynamics and intentionally induce subterranean movement.
So, let's systematically break down their methodology from the 4-day experiment in April. Step 1, drilling boreholes directly into the solid rock walls. Step 2 is the crucial catalyst, injecting 750 cubic meters of water right into a pre-selected fault that's been meticulously wired up with sensors. And step 3, which you must highlight in your answers, is the strict safety protocol. Absolutely no human presence was allowed in the tunnel during the fluid injection. Everything was monitored entirely remotely from ETH Zurich, which really demonstrates the exact standard of ethical scientific administration we expect in high-risk experiments.
Now, aspirants, please note the sheer scale of the outcome here. A staggering 8,000 microseismic events were induced during this trial. That's a huge number. And crucially, the fluid injection didn't just trigger the targeted fault, but it successfully sparked localized movements along other faults running completely perpendicular to the main one.
This resulting data yields a very important lesson for your mains answers when discussing scientific evaluation. The magnitudes recorded ranged from -5 to -0.14. Now, yes, they fell just below their specific target of a magnitude 1 earthquake, but Dr. Giardini still considers this a massive success. Achieving unprecedented deep-scale data like this remains a critical breakthrough in applied seismology. As they noted, this has never been done at this scale and never this deep.
As seismologist Ryan Schultz so aptly puts it, this is kind of pushing the frontier of science. Oh, absolutely. Specializing in human-made earthquakes represents a true paradigm shift in disaster mitigation strategies. These researchers are taking highly theoretical models of tectonic stress and they are translating them directly into subterranean reality. It's brilliant.
And to translate those abstract numbers into physical reality, Dr. Giardini mentioned that anyone standing near the fault would have flown in the air with a big jump. Think about that from an analytical standpoint. A -0.14 magnitude generating 1.5 times standard gravity acceleration. It clearly demonstrates the immense localized kinetic energy contained right within these subterranean fault lines.
Now, what's really interesting about this slide is how it connects to a core pillar of your GS3 disaster management syllabus, risk mitigation. We have to rigorously contrast that violent 1.5 times gravity acceleration happening deep underground with the absolute safety maintained at the surface level where literally nothing was felt.
Exactly right. By carefully lubricating the existing fault, the scientific team temporarily added only about 1% to the natural baseline risk. It proves how highly controlled subterranean stress testing can actually be executed without endangering any civilian populations above ground.
Aspirants, if you get asked in your mains examination about future technologies in proactive disaster prevention, this is your key takeaway. Dr. Giardini clearly defines the ultimate goal here. If we master how to produce quakes of a certain size, then we know how not to produce them. It makes perfect sense. By deciphering the precise mechanics, the injection angles, and the fluid pressures required to trigger a microquake, scientists can effectively reverse engineer the entire process. This controlled mastery is quite literally our roadmap to preventing large-scale, devastating natural earthquakes.
It really is a remarkable evolution in scientific capability. We are no longer just passively waiting for the Earth to act. We are actively querying its parameters.
So, as future administrators, I want to leave you with this assignment for reflection. As we push the extreme frontiers of science, how else might we safely simulate today's complex hazards to prevent the catastrophes of tomorrow? Keep this perspective sharp for your GS3 preparations.
Thank you for joining this detailed analysis. We wish you the very best in your UPSC preparation from all of us here at Rungta IAS Academy.